towards mid-level image processing. So low-level image processing, what we said was basically that your input will be also be image, output will also be an image, either an enhanced image or filtered image or edge image or whatever. So all the previous operations that we have discussed so far were kind of a low-level image processing operations. Now we'll move to mid-level image processing. So till your next sectional, we'll be basically covering topics which come in mid-level computer vision or image processing. So there basically we'll take input will be an image, but from the image we will be trying to extract some useful properties of regions in that image, either related to shape, structure, or some interesting features which you can use for matching objects in an image and so on. So we will spend time now on that till second sessional, and after second sessional we'll try to move towards the high level image process, high level computer vision algorithms. So the first topic which gets used so many a lot frequently is morphological image processing. So the topic that we are going to discuss is morphological image processing. This is basically applicable on binary images. So we are going to discuss what do you basically mean by morphology and what are different morphological operations, and some algorithms and applications based on those operations. So literally the term morphology, what is the literal meaning of morphology, or the word morph, I think you would have, yeah, kind of to so it's related to the shape and the structure of the, so it's a Latin word which is relates to shape and structure, so transforming shapes and structure of the things. So here also we will be basically using this, so the morphological image processing operations are basically techniques which are useful uh, for uh, for description, for basically extracting image components that are useful in the representation and description of region shapes such as boundaries, skeletons, etc. So what basically it means, we'll have a 2D binary image with different object shapes, let us say different types of, there may be a binary image with different objects regions there. You may want to count the number of objects, you may want to count which are square objects, which are rectangle objects, or you may want to extract the boundaries of the objects and so on. So all those things which are useful for in some way to characterize your objects or regions in the image, especially in terms of its structure and shape, that all those techniques generally can be done in this set of morphological image processing. And another, that is one important reason, and another reason why these operations are used, they also act as kind of a post processing operations. So there earlier what the image enhancement operations that we discussed, they were kind of a pre-processing operations, noise removal, enhancing the contrast, all those things. So before you start applying algorithms, before you start doing any mid-level or high-level operations, generally you pre-process images, you try to minimize the noise content, you try to enhance the contrast and all that, so that your algorithms will reasonably give better output. Whereas these morphological image processing operations are generally used as a post-processing operation. So once you do some operations like segmenting regions from an image, there are sometimes imperfections introduced during that process, and we'll see an example. We can remove those imperfections also by doing these morphological operations. So a quick example is here. Let us say this image is given to you, a grayscale black and white grayscale image, and you do a thresholding operation. You basically do a thresholding operation, then you will get a binary image like this. So you choose a threshold value, any intensity value greater than that, you'll make it 0, and less than that you'll make it 1, and so on, or vice versa. So you may get this kind of an image. Why you may want to do this kind of image? You may want to count this number of object regions in this image. How will you count? You run a CCL algorithm, and you can get a count of number of objects, distinct objects here. You can count. You can get the area of each objects. You can count the number of objects with label 1 or number of objects with label number of pixels with label 2, so on. You will can get the area of each object and so on. So those are like some quantitative properties of different shapes here. So those things we can do, but the problem is when you do a thresholding here, you get some imperfection. One imperfection example is shown here, because as you can see, you are assuming here that all images are darker than the background, so you would have chosen appropriate threshold value in between. But because at the ring and the circumference of the ring of this, there is this ball bearing or whatever, I don't know, has some white portions here. So because of that, the threshold has not worked properly fully. This object, some pixels in this object are missing. So if you simply run a connected component algorithm, this may cause problem. You can guess why, because there may be different, you may get multiple regions here itself. So ideally you should fill up these pixels and then run a connected component algorithm. Then it will give a proper result. So one example we'll see to how we can very easily fill up these things by using a morphological operations. You can do any other way. You can guess any other way. You don't know morphology right now, but let us say you have this image. How can you fill up these pixels? So if you knew the boundaries of this, then it would be probably easier to fill up. But how will you come to know the boundary? Hmm? Edge detection. Okay, that is a good suggestion. We can try to do edge detection. But as we said, edges, we may not always get a connected edge. So you may not get, it may not always be give you a robust result. Even the edges may be there may be missing pixel in the edges itself. So we'll see. So that is a good thing. We'll see. Last time before starting this topic, I discussed methods by which we can link edges, Huff transform and all that. But I'm right now postponing it because I'll combine it with some other similar topic later on. So after you detect edges, you can actually try to connect missing pixels to generate some. But that topic will I will be postponing a little bit here. So, but the idea is not so straightforward to fill this missing pixel. Although the question remains very simple, but to fill this missing pixels, it's not a very straightforward method to do that. But we'll see with morphology, it becomes a very straightforward way to do this. This is another example of a fingerprint image. So normally when you do fingerprint recognition and all that, you take the image and then do a threshold segmentation. So after segmentation, invariably you get this kind of an image. So along with the fingerprint ridges, you also get many imperfections, either some noise pixels here or some holes in the fingerprint ridge itself. So before you can actually do fingerprint recognition, matching these fingerprint things, you would ideally like to get rid of this noise and all those things. So we'll see one a very elegant way of doing this thing is using morphological processing. We can get from this image to this image very easily. So formally speaking, morphological operations are defined in using the set theory notation mathematically. So if you define a set A as a set of pixel locations x comma y such that the intensity value or the image value at that location x comma y has is belongs to certain value. Let us say if it is a binary image, we can decide. So let us say A represents all those locations in the image where the image intensity value is 1, or we can have another set B where the image values are 0, and so on. So we can we can use set notations to describe image regions in a binary image. So right now we are limiting our discussion to binary image itself. Later on also we'll see morphology can also be discussed in terms of grayscale images. But for most part of the discussion, we are going to restrict our discussion only to binary images. So intensity values are either 0 or 1. So we can use set notations to basically represent different regions in an image. So let us say we have one set A as this and another set B with some other things, and then we can use operations like standard set operations like union, intersection, set difference, set complement. Also we can define with that. So once we define sets in an image, let us say this A is a set of pixels in this region and B is set of pixels in this region. Then we can do a set union operation. Then we'll get set of pixels in this combined region. Similarly, if you do a intersection operation, then we'll be left with pixels in this intersection area and so on. If you do a complement, we'll have the background pixels, and if you do set difference, we'll be left with this image. And similarly, we can use logical operations also, like and or not on two sets. So if set A is this, set B is this, we can use A and B. That will basically give you set intersection kind of thing. If you use A or B, it will be union. And we can use A or B and so on. A complement can be implemented using not operation and so on. So by those things can be straightforwardly. So these are usual notations. Apart from the usual notation, there are two other important set operations which we'll be using in our subsequent discussion. One is reflection on a set and a translation on a set. So set reflection basically means reflection of a set B. The operator is basically this cap over the set B, is a set of all elements W, where W is basically equal to minus of an element B coming from set B. So what does this basically means? So if we take all the elements, set B is our previous set that we were representing here. This is our set B. So this set was basically something like this. So around origin, basically, if you reflect it, so if you take all those elements in this set B, take a reflection, basically minus of B basically means it will reflect around the origin. Then you will get this reflected set B cap. So B cap is basically meaning is defining a reflection of a set around an origin. So wherever you define origin, reflection will be basically all will be this set. And a translation of a set A is represented as A subscript Z, where the content of this translation of set A is obtained by taking all the elements from the original set A and adding this offset of Z to each element to get the resultant element C. So if your original set was something like this, if you take all those elements here and let us say Z is has component Z1 and Z2. So to each element of set A, if you add Z1 and Z2, then you get a translated set. That means the set A has been translated by an offset of for vector Z, and that is defined as translation operation on a set A. So it's a similar thing, not different, but so is there any doubt here? Set reflection and set translation. The intuition is clear. In set reflection, we'll be reflecting along the origin and translating it, and in set translation, we'll be translating it by a fixed value. Why we are discussing this mathematical notations, because if you want to formally define those operations, we will use these set notations. Otherwise, we can even informally understand what it means. One final thing before we discuss operations, morphological operations. All morphological operations are defined using a structuring element. What is this structuring element? This structuring element is similar to the filter or the kernel that we were using for correlation convolution operation. So, but the term used for morphology in morphology operation is called structuring elements. So these structuring elements basically are small sets of sub images which we'll be using to probe an image under study. Basically, just like when we were taking a particular Gaussian kernel or particular derivative kernel or filter, we were applying the correlation operation on the image, and we were getting an appropriate result according to the kernel. Similarly, here also we will be defining an appropriate structuring element, which is also again a kernel or a filter kind of thing, which is a small set of small sub image. And again, we'll be basically doing the same operations like that. Uh, Now, why it is called structuring element? Because depending on the size and the shape of this set, you will get a different result. You will manipulate the region shape and structure according to the structuring element that you choose, according to the shape and type of this structuring element. So for each structuring element, we first of all define its origin. Origin can be either in the center or it can be anywhere. You are free to define where the origin of you want to define for it. And also you have to define its shape and size. So you can define a simple rectangle or a square structuring element, or a cross structuring element, or a diamond shape structuring element. And also you can have a size of 3 by 3 or 5 by 5 or 5 cross 1 or whatever. So you need to define its, you need to choose first of all its shape and size. And normally, as I said, the shape and size will be suitable to the geometric properties that we want to manipulate in the original image. So we'll see examples of this, then it will become more clear. This the stage and site will has some correlation to the how to the geometric properties of the objects. Now, irrespective of what structuring element you choose, what shape and size structuring element you choose, the way we will implement is again using uh, a square kernel. For example, if you want to represent this cross structuring element, we can represent this cross structuring element again by using a 3 by 3 filter with all these values as 1 values and all these values as 0 values. Similarly, this diamond shaped structuring element also can be represented by using 7 by 7 structuring element with all these shaded ones as 1 and white one as zeros. Sorry. Okay. One other informal thing that I want to discuss here, because this will make it easier to understand how this operations, the operations that we will be discussing. We will take these structuring elements and we can place it at overlap it at different locations of an image, just like we were doing correlation convolution operation. And at each location, we can try to see whether this structuring element is exactly fitting that region in the image, or it is just hitting that region in image. So what is fit and hit? So this you won't find in book, but this was some useful explanation that I found in somewhere. So I have taken it here. So fit basically means if you take structuring element, place it at, for example, if you take this structuring element, if you place it at this location, then all these shaded values of locations of this structuring element are overlapping with all the shaded values in the image. So when all on pixels, on means shaded pixels or 1 pixels in the structuring element cover all the on pixels in the image, we are saying that it is exactly fitting that location. And if it at least hits one look, if there is at least one image, one such pixel locations, so here at least one of the location is, one on pixel is overlapping with at least one on pixel, then we'll say it is hit. So if any on pixel in the structuring element covers an on pixel in the image, we will say it is this structuring element is hitting that location. So for example, at location A, it's exactly fitting. At location B, we will say it's a hit, and at location C, there is neither fit nor hit. So let us become more thorough with this. So let us say these two structuring elements, structuring element 1 and the structuring element 2. So at this location, at location A, the structuring element 1 is a hit or fit, and what about structuring element 2? So, so if it is fitting, it's automatically hitting. When it is fit, completely fit, then it's also hit condition. So, uh, so for stretching element 2, first see whether it is fitting or not. If it does not fit, whether there is a possibility of hit, and if not, then none of these things. So whether it is fitting, so it is fitting. So it is both fit and hit, because hit is actually kind of a subset of. Huh? No, fit is not a subset. In fit, your all on pixels should overlap with all on pixels. Whereas in hit, only if even one on pixel overlaps, it's a hit. Every hit is a fit. Every hit will. Nah, huh, that is the way you are saying. Okay, okay, I think you have got the point. So, okay. So the way you say it will differ, so it doesn't matter. So, okay, for structuring element 1, it's a fit. For structuring element 2, it is also fit, nah? Because we have to only consider on pixels. So all on pixels are overlapping with all on pixels. So it's a fit for both stretching element 1 and 2. What about B? For stretching element 1, it is only a hit. It's not. And what about stretching element 2? It's a fit for stretching element 2. What about C? So for 1 it is hit. For B, neither hit nor hit. Okay. So now we'll come to the main operations of morphological, the building blocks of morphological operations. The two fundamental operations are called erosion and dilation, and the dynamics will remain similar like we were doing the filtering thing. We'll take these structuring elements, we'll basically put at every locations of the image, and we'll decide whether it is a hit or fit. So for erosion operation, formally speaking, erosion operation is defined between two sets A and B, where A, one of them will be your original image. A, let us say A is your original image I, and B is your structuring element. Then we say that I'm eroding I or A with B. Erosion of A with B basically means taking that set B, translating it by Z, and then seeing whether after translation whether that set is a proper subset of A. Proper subset of A means it is a fit. If it exactly fits into that set, then it is a proper subset of A. So, this notation basically says it is a set of all points Z such that B, when translated by Z, is fully contained in A, is fully fitting into A. So informally, if you want to understand this, you take the stretching element B, position its origin at any location x comma y of an image, and try to see if at that location B fits A. If B fits A, then you will output there 1, otherwise you will output there as 0. So the result of fit operation will be 1, and if it is not fitting, it will be 0, because your set should have only those locations where it is fitting. So only those locations where it is fitting, it will be 1, and all other locations it will be 0. So an example, let us say here, let us say take this structuring element, this cross structuring element. On pixels are these shaded ones, the blue ones, and these are original image with on pixels this shaded dark blue, and background is your light blue. And if you do origin operation on this using this structuring element, what should be the processed image? So what you have to do, you have to take the structuring element, put at every location and see whether it is fitting or not. So at this location, no. This location, this location, no. This location, how many shades? Yes. So it's hitting, but for erosion operation we have to consider only fit. So it does not fit. So it will all these locations will be 0. Where it will be 1? Will this location be 1? No. So all these location will be 0. In the next row, this is the first location where it will be fits. This will be another location where it is. So here also it will be 1. So this will be 1. This will be 1. Here it is not fit and so on. Again here. So this will also be. This will be 1. This will be not 1. This will be 1. And all will be 0. So that means the output image you will have this location as 1 and all of them will be 0. So the green one is just highlighted to show that this has been subtracted from the original image region. In the actual image everything will be 0, only this will be 1. So why we are calling it erosion? Can you understand this? Why we are calling this operation as erosion? Hmm? Why only top? So it is eroding away pixels from the boundary. This erosion operation is basically what it is doing essentially. It is chipping away pixels from the boundary pixels. The boundary pixels are getting chipped away, and how many boundary pixels will chipped away and which boundary pixel will chipped away, that will depend on the structural element. So let us say if you have chosen all these ones, instead of diamond you have chosen this cross, you have chosen a square structuring element, then do you expect more pixels to get eroded or less pixels? Huh? You will get more pixels to be eroded. There will be less fit positions. There will be more. There will be even fewer. Only I think only one of the locations may have. No, I think none of this. Huh? ये वाला. This only you'll be left with this one, and every other locations probably will get eroded away. Well, will get be removed. So depending on how what shape and size the structuring element you choose, that many pixels will get eroded. So we'll see more examples. So let us say this is the original image. If you erode it by a 3 by 3 square structuring element, you may get this kind of an output. If you erode by a larger size 5 by 5, you will get the further more images pixels will be eroded from the boundary. Now the notation whether it is black is 1 or white is 0 1, you will use it interchangeably. It doesn't matter. The set that depends on what you define, how you define. So where we'll apply this erosion operation? Erosion can have these uses. For example, sometimes your two different regions may be joined together, and so if you run a connected component algorithm, this will be form part of a single region. But ideally, you would like them to be. These are two different regions. You don't want them to be a single region. So you can run a small erosion operation so that at least one pixels are eroded away. So they will be splitted away. So this post processing will help you in splitting away objects which get accidentally merged either due to some operation, some noise or whatever, or sometimes for smoothing the shapes or the boundaries of the pixels. So if for example in this image, if you run an erosion operation on this image, you will get a nice circle here. These protrusions, extrusions can be easily removed by choosing an appropriate structuring element and doing a erosion operation. So now a quiz for you. If you have this image A of size d by d, and if you have stretching element B of size d by 4 and d by 4, the output shapes will be of size and shape what? If you do an erosion operation of set A with this set B, from each side, how many pixels will get eroded? It's a square stretching element, so it will uniformly erode from all sides. Eh? So from each side, so where it will fit exactly, it will fit at this location. Sorry. So where the first location where it will fit will be this location. This will be at a distance of d by 8 from the leftmost edge. Similarly, from the top also this will be a distance d by 8. So this will be the first on pixel. From here onwards you will get 1 pixel. Similarly, at here also you will be eroded. So d by 8 and d by 8 from each side it will get eroded. So the leftover object size will be of size 3d by 4 on each side. If you had this stretching element, it's a rectangle stretching element, d by 4 width and d as the length, or then from this side it is d by 4, so that means this d by 8 d by 8, but from the top and the bottom it will reduce by d by 2 and d by 2, so you'll be left with only a single pixel line. Is that clear? Let us say if we change the origin, let us say if we place this origin here, if we take this stretching element itself, if we take the same stretching element of size d by 4, but the origin now is not at the center but at the top left corner, what should be the output? Hmm? So the size will be the same 3d by 4, huh? But it will be, this entire thing will be shifted towards this. What is happening? Control P. So it will be basically shifted towards the corner because the origin has been changed. So the way you define stretching element, the output will be different. Where it is origin, what is size and shape. So this is a simple example of applying an erosion operation using a disk stretching element. So here the stretching element is a disk shape stretching element of some radius 15. So first, if you apply of a radius 11 by 11, then it has removed all those fine or thinner lines. The thicker line has survived. If you increase the radius to 15 by 15, even the thicker line has been removed. And if you increase the radius further, even these pins have been eliminated. So depending on what you want to remove from here, you can choose the size of the stretching element appropriately. If you repeat the erosion operations, if you iterate it more number of times, more erosion will happen. Or you can directly use the larger size stretching element and do it just once. A complementary operation to erosion is called dilation. As the name suggests, instead of eroding away here, we will try to add pixels to the original image. And the way dilation operation is defined in literature is like this: you take the set. So A is the original image I and B is the stretching element. You first of all reflect the stretching element B around its origin. Why this is done, I will not give you full detail, but just an intuition for that. Now take that set, translate it by Z, and see whether it is having some intersection with A. That means at least one pixel is there matching. If at least one pixel matches, then that pixel will be included in the set. So that means here we will see a, instead of fit operation, we'll see a hit operation. We'll take the searching element B, go to every locations and see whether it hits any location of A. If it hits, that location is 1. Why we are doing this reflection of the set B? That is for a reason, because when the dilation operation is defined this way, and then actually it gets some useful properties. The combination of erosion and dilation actually becomes kind of a dual. They assume a dual nature. We'll later on also see that using these erosion and dilation operations, we get other operations. And if you don't take this reflection, then the dual property is not maintained. So that's why I think for that reason this set reflection is done. But it doesn't matter, because most of the time stretching element that we'll use are symmetric, and most of the time the origin is at the center. So whether you reflect it or not reflect it, you get the same stretching element. So most of the time it will not make a difference, but just sometime a tricky question may be given, the origin may be shifted somewhere here and there, and if you don't reflect it, then the output will be different. But for most practical purposes, it really doesn't make much difference, because almost all the time we choose origin at the center and we use almost a symmetric stretching element. So if you take this stretching element and take this original image here, and if you apply dilation operation, what should be the result? So again take this, run over it, where it will be 1 first. Here it will be 1. No. Here, yes. So this location will become 1. This location will also be 1. No, not 1 here. This also is 1. Okay, okay. So here it is 0, 0, 0. Here also 0. Here it is 1. So if you see later on, here also it will add 1. So on the boundary, it is going to add boundary. It is going to add 1, 1 location. So if you continue on doing this, it is basically going to give you this process image with dilated pixels. So your original boundary you will be adding 1 pixels from each boundary. We have used a 4. This cross stretching element is basically considering only 4 neighbors. So we have added boundaries only in the top and the left direction, not in the diagonal direction. So if you use a square stretching element, then even this diagonal will get filled, isn't it? In the middle also, this will also get filled, yeah, because then it will be considered all direction. So just analogous to structure erosion, if you apply dilation, they are going to grow up. Stretching, I'll just quiz is there. So the application of this dilation operation many times for this text recognition, when you take the scanned image, scanned document, and you threshold it, the text gets broken because of noise and all that disturbances in the. So your text may get the characters may get broken. So if you do a dilation operation on this, they will get connected, and now you can extract these separate characters easily. Earlier you cannot extract this as a one connected region. So by doing this post processing with this dilation operation, you can ensure that this splitting thing is taken care of. You merge the different splitted parts into one connected components, and then extract them. Just analogous to the previous example, if you are using a structuring element this, it is going to add d by 8 di by 8 from each directions, and here it will going to expand it. So Shika's question here, so if this is your original image I and this is your structuring element B, and the origin is at the center only here, what should be the result of this dilation operation? What should be the result of this dilation operation? Where should be 1? Where should be 1? This is the same thing when we discuss convolution operation and correlation operation. In convolution we would flip the searching element, do this, and by doing that convolution operation gets some additional properties which are more useful. It makes it commutative operation and so on, whereas correlation is not that. Similarly here, that is the reason why this is also defined it that way. Now use the set notation thing. All elements becomes, if you take B from set element B, then you have to take minus of B. So minus of B means x will also become minus x, y will also become minus y. So the x and y component will become minus 1. So it is basically going to, so the first quadrant will go to third quadrant, second quadrant will go to fourth, fourth will go to second, and so on. So the result will be like this. This one is going to come here, this one is going to come here, this one will going to stay here. So this will be your reflected set. And if you do this dilation of this on this, what will be the result? So these will remain as it is. Additional pixels will be added where? Where? Here or here? Huh? Here, huh? What about here? Dilate on both sides. Right now it's only dilating on one side. If you want to do that, that depends on your purpose. So in that case, you will directly use the symmetry structure and just do it one. This is just a thing to just test your this what you get theoretical understanding of that the definition of dilation. So again, it is going to use for to repair the breaks. It is going to use to fill up missing pixels and so on. So remember the original image that is the first image. There were missing pixels in the. How can you fill up those? You can just run a dilation operation. Combined with erosion, it can eliminate irrelevant details. That is another example here. So if you have this, suppose we want to only, this is a similar problem that we discussed earlier. If you want to only, if you are only concerned with areas or objects with larger size, with significant size, and we want to get rid of the smaller size things, what can we do? You first erode, then erode. So let us say if you want to, if you are only concerned with squares of size 15 by 15, then take a erosion filter of just smaller size than this. So if you take a erosion filter of size 13 by 13, then every other locations will get fully eroded. Only some of the pixels of these locations will be remaining. But if you want to restore them to their original size, then again do a dilation of with the same stretching element of size 13 by 13. So these will get restored to their original size. But effectively you have got rid of this irrelevant small size locations. So what happened? So you got this idea. So if you, by combining erosion and dilation, we can serve many meaningful purposes, and we'll discuss in the next class what are the different applications we can do.